All right, now let's look at this function over here. Here we actually have two functions. Let's look at z is equal to, let's look at this z is equal to square root of 25 minus x squared minus y squared. Some of us may already know this is going to be a sphere. Why is that? Because x squared plus y squared plus z squared actually appears in the distance formula. If we are in a three-dimensional space, suppose you have over here x and y and z over here, then if this coordinate over here is x, y, z, then the distance over here by Pythagorean theorem, this d is actually d squared is equal to x squared plus y squared plus z squared. So immediately we know, so we're going to use this one as a radius and then draw a graph, a surface, so that the distance to the origin is a constant. So we know it's going to be a sphere. But on the other hand, can we actually say use a different way to see this is a sphere? The method we're going to discuss over here is, say, we're going to use the intersections of this function with different values of z. So we're going to try to see, if z is equal to 0, what kind of things we have. So if z is equal to 0, we have x squared plus y squared is equal to 25. And then we know this is a circle, right? So we're going to try, so this one over here. Now, how do we draw a circle? Because this is three-dimensional, so we cannot really draw a circle. We can only draw an oval over here. The radius is 5, so we can draw something like this. Okay. Now, if you look at what's happening over here is that you see that because z is equal to square root of 25 minus x squared minus y squared, right? So we will see that the domain over here is 25 minus x squared minus y squared must be bigger than or equal to 0. So in fact, this one over here is our domain as well. Okay, so z is equal to 0. Now, if x, y is changing between this domain over here, we see the z value actually z value is changing, right? If x, y is equal to 0, that's the highest point. This is the maximum value, max. And max is going to be 5. So z can only reach 5. And then for different value of z, we're going to have circles again. For example, if z is equal to 3, then we're going to have 9 is equal to 25 minus x squared minus y squared. That will give us x squared plus y squared is equal to 25 minus 9 is 16. So we have a circle again. This is another circle. So what we see over here is another circle like that. And the circle gets smaller and then reach the top when x is 5. So we actually have an upper hemisphere. Okay. And this is roughly the method we're going to graph some simple functions. Now, in chapter 12, we have an entire section on how to graph these so-called quadratic surfaces. We have basically 6 different types. The last one over here is so-called a degenerate one because you have 0 over here. And of course, you can choose different coefficients. But let's just use the last one as another example over here and try to see how we can actually graph it. You will see again, we're going to use the method of choosing different value of z. Okay, it depends really because we know x squared plus y squared equal to z squared. We know this is going to be a circle, right? This is going to be a circle for different value of z. So what we see is that if z is small, then we have a small circle. If z is bigger, then we have a bigger circle. And this radius actually increases. And if z is negative, we have again a small circle first and a bigger circle, and like that. Of course, this won't be really a big, a very nice one, but it's not too bad. As you can see, this is going to be a cone, right? Okay. So every surface over here we listed can be done in this way. We look at the cross sections of these surfaces with special planes, coordinate planes, or planes with a constant z, or constant x, or constant y. And that way, when we draw the intersections, we somehow can visualize what kind of graph we have for this function. Now, the ones we listed over here, they are not put in the explicit function form because you have z squared, and we know how to solve them, right? For example, if this so-called elliptic paraboloid, and then we can write down as a function, z is going to be equal to 25 minus 9x squared and minus 4y squared. And then we can actually graph roughly the surface that's determined by this equation. All right, let's stop over here for the graphing.